Okay, we're looking at the limit definition of the derivative, and I don't know if that's what your instructor is calling it, but that's what we're doing, right? So we're finding a derivative, which is an instantaneous rate of change. Basically, how fast are we changing at that exact point on the curve? Um, and we're using the limit definition of that. Long story short, basically, we're going from an average rate of change, which is like, okay, over this interval, how fast was I changing, to we're getting smaller and smaller and smaller and smaller and smaller until we're saying, how fast am I changing at that exact point? Okay, so that's why we're doing the limit as h approaches 0, because we're saying like h is getting smaller and smaller. H is this distance between our 2 points. And eventually we're going to say when h is 0, when these 2 points are actually the same point, where are we approaching? Okay, so that's the idea. And you noticed a really interesting concept. You notice that sometimes it seems like we were just taking the exponent and multiplying it by the numerator, but sometimes it was negative. And it was interesting to kind of think about. So you did actually find a rule for derivatives. And that rule works for all derivatives. And we're starting with the limit definition and moving into that rule. And I know it seems kind of silly because this rule is going to be so fast and easy, but it's kind of like you have to learn how to multiply by hand before you can use a calculator. It's just because you need to know and understand where it comes from and understand limits. But yeah, so what you found was that if I said if f of x is 3x to the fourth, then the derivative, if I did the whole limit definition of derivative here, it actually would turn into 12x to the third. That's the derivative, right? If I wanted, so if I had a different function, g of x, that is 6x to the third, g prime of x would be 18x squared. And so you notice the pattern is I take the exponent and I multiply it by the number in front, and then the exponent loses 1, or we subtract 1 from it. One thing I wanted to point out that you had a question on is the g prime versus f prime, or f and g. And they're just different ways to name functions, right? So back in the day when we first started, we would say something like this: y equals 6x to the third. But as we get further and further, what happens is we use more than one function in a problem, and sometimes we even use a different exponent, or not exponent, a different variable. So instead of x, we're using t, or p, or anything else, right? And so this is just a better way to name functions. Instead of saying y equals, we say g of x equals, or f of x equals. There is absolutely no difference between f of x, g of x. It is completely arbitrary what number we choose. We typically choose f because mathematicians, I don't know, we like consistency. And so we do that. But you can name it anything you want, right? And there is absolutely no difference between any of the letters. And you can even see something like g of t. And that just means that instead of an x there, you're going to have a t. And that's it. It just means that's the number that's going in there. And so then you might be wondering, well, what about this one that we had? How does that rule that I just told you, how does it work for this function? Well, what you might remember, and it's okay if you don't, is that we can write exponents as negative exponents. So if they're in the denominator, a positive 2 exponent in the denominator is the same as a negative 2 up in the numerator. So when we cross the line, we change the sign. So this 3 over t squared is the same as 3 times t to the negative 2. So if we use the same rule that I just told you exists for that one, we would take the negative 2, multiply it by the 3, and we'd get negative 6. And we'd subtract 1 from negative 2. Well, negative 2 minus 1 is actually negative 3, right? And there we go. And so could I rewrite that? Yeah, I could. Negative 6. And then remember, this t to the negative 3 is the same as t to the third down in that denominator. So that is what we figured out was the answer with the limit definition. And I know that that's like crazy quick. But we will get there to this rule and all the other rules and the product rules and things like that of how we find these derivatives that way. But for today, we're doing the limit definition. So let's look and see what that looks like for this one. So we're starting with 3 over t squared. And remember, the limit definition says that the derivative, I should have given myself some space here, but let's just say, and I'm going to write it the way we're supposed to, f of t. It's typically how we'd write that since t um, is our variable. We typically wouldn't write f of x. It's not a big deal if you do, but you know, mathematicians, we like to be precise. So if this is our function and we're looking for the derivative of it, we know that the derivative, and remember that's that little like apostrophe, we call it f prime of t, is the limit as h approaches 0 of f of t plus h minus f of t all over h. There's a whole explanation about why this works, but if you can just think about it, this is the change in y over the change in x. So it's the slope of a line, and again, we're talking about as these 2 points, f of t and f of t plus h, right? So these 2 points that are apart from each other, as they get closer and closer together, what is the slope of the line at that exact point? So that's really where this comes from. So again, what we are going to do is we're going to figure out what is f of t plus h, right? And so that's not too hard, right? We just, instead of a t, we just have a t plus h. Everywhere there was a t, we make a t plus h. Okay. So now what we're going to do is we're going to find the limit as h approaches 0 of, let's see, f of t plus h, so 3 over t plus h squared, minus f of t, which is just 3 over t squared, all over h. Okay, so this is what we're actually going to find. Now, the first thing that we need to remember from algebra is we don't really like fractions inside of fractions. They freak us out, you know, even though fractions are our favorite F word. We really want to get rid of them right here. So the way to get rid of fractions is to multiply by a common denominator to, you know, cancel out those denominators. But again, we remember that with fractions, we have to multiply the top and bottom by the exact same number. Otherwise, we're changing the fraction, right? So if we multiplied this by 2 over 2, that's fine, because we're really just multiplying by 1 then, right? Because 2 over 2 is the same. So we think, what's the common denominator here? So the common denominator is going to be this denominator times this denominator, right? So we're going to say t plus h squared times t squared. That's our common denominator. And if we multiply the top of this fraction by it, we also need to multiply the bottom of this fraction by it, okay? So I know it's like tempting to want to like multiply all this out. I tried that and it was really messy and it ended up being so much worse. So for now, we're just going to leave it. And I know it's hard to like know when to do that and when not to. I would say leave it unless you have to expand it. So we're going to multiply this in. And so remember, when we multiply across addition or subtraction, we multiply by each term, right? So this multiplies by this term and then by this term. So what we're going to do is I'm going to write the whole thing out, right? So I have t plus h squared. This is that first term. And we're going to multiply that by t plus h squared times t squared. Sorry, my tablet decided not to work tonight, and so I'm having to do it a different way, and it is not nearly as neat and pretty, but that's okay. So we had this one. This was our second term, right? And then we multiply it by t plus h squared, t squared, right? So all I did is take this, multiply it by this and that, and then this is going to be all over h times t plus h squared, t squared. Okay, so it looks uglier right now, but what we recognize is I have this on top and this on bottom, and that's what I was hoping for, because now they cancel out because they are the same term. So I can cancel those two out, and I would be left with, we'll write it up here, 3t squared, right? Because there's nothing in the denominator now. And same here. This, we notice we have a t squared on top and a t squared on bottom, so they cancel out. Again, that's what we were going for. So now we have 3 times t plus h squared. And on the bottom, we're just going to leave that all icky for now. Okay, I haven't been bringing my limit down, but you know, we're doing the limit as h approaches 0 of all of this. Okay, so now, like I said, we don't want to expand until we have to. We have to expand this now. because we can't simplify any further. So what you might remember from algebra is that when we expand something like t plus h squared, that really means t plus h times t plus h, right? Okay, and there's something called FOIL that we did first, outside, inside, last, right? Or you can just think of each by each, right? So this t needs to multiply by the t and by the h. Then this h needs to multiply by the t and by the h, right? So let's start. T times t, okay, well that would be t squared, right? T times h is th. H times t is ht. And then h times h is h squared. And remember, multiplication is commutative, which means that h times t is the same as t times h. You can 3 times 2 is the same as 2 times 3, right? So these are actually the same thing. So I actually have two of them, right? I have 1th and 2th. So I'm going to write this as 2th plus h squared. Okay. So that's just that expansion of the multiplication. So we're going to bring that back here and we're going to say, all right, 3t squared minus 3 times, now I just put in what I expanded here. So that would be t squared plus 2th plus h squared. Okay. And now I'm going to distribute in. So I had to do exponents before I do multiplication. That's a big one in order of operations. You have to expand this first. You can't bring the 3 in first. It doesn't work. It just is illegal. This exponent is stronger than that multiplication. So you got to do the exponent first, right? It requires you. It is it doesn't like to go second. So don't make it, go second. So we're going to do that. We expanded it first by multiplying that out, and now we're going to bring that 3 in. Now remember, this is a negative 3, right? Because it's minus 3, and so these are each going to be multiplied by negative 3. So we're going to do 3t squared, right? And then negative 3 times t squared is negative 3t squared. Negative 3 times that would be negative 6th. Negative 3h squared all over all of that. Okay. Now we notice that we have 3t squared minus 3t squared. That is 0. So now I'm down to negative 6th minus 3h squared over all of this. And this is where, when you're doing the limit definition of the derivative with this h, you should at this point be able to cancel out an h everywhere, right? Because this h in the denominator is a problem. Because if I put h in here right now, remember with direct substitution of limits, I can put I could say the limit as h approaches 0. I could just try putting a 0 in, but the problem is I'd get 0, 0, 0. That's called the indeterminate form. And it's like, it means that there's a hole in the graph. It means that we can approach it, but we can't actually get right to it. So we've got to do something, and so you should be looking at this point, you should be able to cancel out an h. So we see we have an h here, we have 2 h's here, and an h here. Now remember, these are all multiplied together, so this h doesn't change anything, right? Because we're only looking at each term. So we say, oh, look, I have an h here. So if I divide each of these by h, I had 1 h and I divide out one of them. I had 2 h's here, so I just divide out one of them, right? So now instead of h squared, I just have h, and I divide that h out. So I end up with negative 6t minus 3h over t plus h squared t squared. And now remember, we're doing the limit as h approaches 0. So we're finally at this point where if I plug 0 in here, I am not going to get 0 over 0. So we're in a good place. So what happens when I plug 0 in here? Well, I'd get negative 6t, right? And then this h, that's going to go to 0, right? So now I've got 3 times 0, so that's 0, right? And then I have t plus, again, this is going to go to 0. So t plus 0 is just t squared. So I'm going to end up with negative 6t over t squared times t squared. Okay. And remember, t squared would be t times t times t times t, right? T squared times t squared would be 4t's. So I'd have negative 6t over t to the 4th. Now I have 1t on top and 4t's on bottom. So one of those t's on top cancels out 1t on bottom. And I didn't leave myself good room, so we're just going to do it over here. and that ends up with t cubed. And that's what we had figured out already. So that is the long limit definition of the derivative.